Welcome. Today, I'm going to be talking about large language models and the future of AI, or what I learned building a really big model. My name is Connor. You can find me at MP Collapse on Twitter and other symptoms of the inevitable decay of our society. As I already said, I'm an AI researcher at German startup Aleph Alpha by day and loose hacker collective Luther AI by night. For those who haven't heard of Luther, we are a loose research collective, aka glorified Discord server, interested in scaling, alignment, and open sourcing ML research. We are most well known for our ongoing project to develop an open GPT-3-like model. But we also do a lot of other interesting stuff. You should come by sometime. So today, I want to tell you a story of 3 GPTs. So some of you may have already heard about the hype around models such as GPT-3. That's probably the one you've heard of, if any of them. And I want to kind of make the point that these models are not just interesting little curiosities, but very much a fundamental shift in how I expect ML and the paradigm of ML to be done in the near future. So let me tell you a bit of the story here. So for those who don't know, the GPT family of models is a family of deep learning models created by the American company OpenAI. And they are outer regressive language models. So what the hell does that mean? So basically what this means is that they are neural network models trained on huge dumps of internet text. So this is everything from forums, chat rooms, Wikipedia articles, just anything you can find, to predict the next word. So there's given the words it has seen so far, it tries to predict the most likely continuation. So it's in a sense a glorified autocomplete. So maybe I would give it a sentence fragment such as pears are, and then maybe it will autocomplete with green or delicious or whatever else the model thinks is the most likely continuation of the sequence it's seen so far. So far so simple. So as I just said, these models are interacted with what's called a prompt. This is not the only way you can interact with these models. You can also do other interesting things, but for our talk, this is the one we're most interested in. So a prompt is the text we condition the model on, we give to the model to continue on from. So in my previous example, pairs are would be the prompt, and then it would autocomplete, whatever else it would do after that. Another important concept to know here is the concept of parameters. So for those who don't necessarily know how deep learning or neural networks work, you can kind of imagine neural networks as these just massive boxes full of numbers, just millions and billions of numbers. And you want to find the right numbers to make your model work well. So you can also imagine kind of like a box with like billions of knobs you can twiddle, and you want to twiddle them so that your model works the best. And so you can imagine that each of these knobs is one of these parameters, one of these numbers, and in these parameters, it encodes, in a sense, the knowledge, the skills, the algorithm that these things ultimately learn to implement. So GPT-2 and GPT-3 came out about a year apart. GPT-2 was kind of like the first one. Again, it got a pretty big media hype for these types of models in particular. So like text-generating models have existed for quite a while, but they were often very, very bad. GPT-2 was kind of the first one that could pretty reliably generate like some really coherent text. Like, there's a famous example about it, like talking about discovering unicorns in South America, or, coming up with, fake political stories and stuff like that. And it was really quite well. You could generally get like a good paragraph of, decent-ish text out of it or whatever, but it wasn't necessarily perfect. And with GPT-3, this just became way more powerful. So you were capable of, making just like, it was much, much simpler to generate really coherent text, very long coherent text. And so you might think, wow, this GPT-3 thing sounds amazing. They must have done lots of really hardcore research and come up with a brilliant algorithm to, make their wonderful model work like this. But one of the most important things about these models is that they're the same model. They're the same architecture, just scaled up dramatically. So GPT-2 and GPT-3 are both autoregressive, called transformer models. What that is doesn't really matter. They're a certain type of neural network model. The only difference between them is that GPT-2 has around 1.5 billion parameters, while GPT-3 has around 175 billion parameters. So that's like a factor of 100. This is truly mind-bogglingly huge, obviously. You can imagine if you try to get all those parameters onto your computer, they are on the order of size of 350 gigabytes of GPU memory would be what you would need to load GPT-3. So it's very much kind of at the limit of what we can currently do with our current compute. So it's kind of wild that just by scaling up the model, just by giving it more data, we got these like really different performance. And this is really something that you only feel when you start using these models. That the difference between using these models is qualitatively huge. So to give you an example, a good friend of mine is working on a GPT-based video game called Project Electric Sheep. Check it out. And the premise of the game is that you enter a keyword and then it generates a dreamscape based around that keyword for you to explore, all generated by AI. So like, text generated by AI, paintings, books generated by AI, a whole world generated by AI is kind of the idea. And one of the things back when I was still working with him on this project is that we wanted to use GPT to generate names for the characters in the dream. And so with GPT, this was really difficult. We had to like create like complicated prompts. We had to make sure, give it lots of examples, have it like follow a list format and whatever. This was kind of difficult. With GPT-3, you could just kind of ask it. Like, I don't know how else to put it. It's kind of crazy. But like with GPT-3, basically we could just write, this is a video game about generating dreams with this keyword. Here's a list of characters. And it just worked. It's not perfect, not every time, but like totally usable and like totally better than any other solution we could have come up with, with our shoestring budget. It totally worked just fine. So this is really the difference between GPT-2 and GPT-3. It is so much more clever in a way. It knew so much more things. It could stay coherent for so much longer and solve so many more tasks. And that, even so, it's fundamentally just the same algorithm, just scaled up. I think this leads to a fundamental shift in a lot of the common knowledge in machine learning, how it is currently practiced. And with the GPT models, what GPT-3 is great, don't get me wrong, but I think what's even more interesting from the original GPT-3 paper was what we found, these scaling laws of performance, of how scaling up these models can make them better. So I like to introduce it with this classic meme here, where we have like the classic ML side, where it's like, oh no, our model is it's over-parameterized, we have to check our bias variance trade-off, we have to do some feature engineering or whatever. Well, with neural networks, just like stack more layers, lol. Just buy more GPUs. So this is, of course, a joke, but also it kind of isn't. So, like, I don't know how to put this, but this really just kind of works. So here is a really fascinating graph from the original GPT-3 paper. So what we see here is on the y-axis is the performance of the model. Lower is better. Just believe me that this number means something. And on the x-axis, we have various parameters of the size of the model that can be varied. So the first one's probably the most interesting. As we give more compute, so just more GPUs running for longer, each of the blue lines is a model of varying sizes. As we go further to the right, the models become larger. And we see that they follow this like trend line. As we get more compute, we get very close to this power law of very predictable levels of performance. We see the same thing with dataset size. As our dataset gets larger, we get this very predictable decrease in performance. So we have to scale the model with the dataset size, to be clear. And with parameters, again, same thing. As we get more parameters and give it more compute, we have this very predictable relationship between the final performance of our model and the amount of compute, the amount of parameters, et cetera, that we put into it. This also leads to this really rather astounding graph that we have here. But what we see here is that on the x-axis, we have the amount of compute that we have that we can give our model. And when you have more compute, you can kind of spend it on three things. You can train on the same data multiple times. You can get more data and train on that. Or you can make your model larger. And really remarkably is that purely empirically, it seems that as we get more compute, as our models start getting really large, it's far more efficient, performance-wise, to build larger models than it is to train on more data. You still need more data for the larger models, but it scales much slower than the actual model size does. So what this means is that as models get larger, they actually become more sample efficient. Ultimately, pretty dramatically so, actually. It's like very large models can actually learn from very, very few examples. This is kind of amazing. Like, I remember that I was taught, when I was first taught, data science and ML and whatever, that, you always want the smallest possible model. You don't want it to overfit. You want it to, avoid, and stuff like that. And that just seems to be wrong. Like, I don't know what else to tell you. It just seems empirically to not be true. At least for this type of task where you have like very large amounts of data and you're doing like pre-training and stuff. This doesn't necessarily apply to every task. Maybe it does, we don't know yet. Like, this is still very new stuff. But at least for this class of problems, this seems that more parameters is just better. Just do as many as you have GPUs. So this is already a pretty clear difference, a pretty large shift in how we think about these models. As a good friend of mine, Leo, put it on his blog, the thing about GPT-3 that makes it so important is that it provides evidence. And as long as we keep increasing the model size, we can keep driving down the loss, possibly right up until it hits the Shannon entropy of text. No need for clever architectures or complex handcrafted heuristics. Just by scaling it up, we can get a better language model, and a better language model entails a better world model. So this is a bit controversial, but I think there's a really good argument to be made that, sure, text is a pretty impoverished modality. It doesn't, you don't really understand, space or colors or reality just from text per se. But if you think about a model that is really, really good at predicting text, it can write stories about characters, it can write scientific papers, it can write these things. I think there's a really strong argument to be made. These models have to understand something about how the real world works. It has to understand, how humans think and how stories are created, or how scientific experiments are conducted, or whatever, in the limit, of course. Now, of course, you could ask whether this will actually scale to some kind of powerful AGI type system or not. And you might say that it might just be necessary that you have multiple modalities. You might need vision, you might need video or audio, whatever. And well, surely this architecture we've been using the whole time can't do that too. Oh, actually, it totally can. So just with very minor modifications to the fundamental transformers architecture, we can see here these are similar graphs to the ones we've seen before, where as the models get larger and they're done on images, on text to image, on video, et cetera, we also see scaling laws emerge. So they have different exponents, there's different amounts of compute. Of course, training a video model is going to cost you, much more computing power than just training a pure text model, but we see the same kind of predictable behavior emerge. This is, to me, one of the most important, just pure scientific discoveries of the last couple of years, in my opinion. It's really phenomenal, and yeah, we're just scratching the surface here with what these models might be able to do in the future. So this would all be enough of a talk, in my opinion. Just scaling laws in themselves, I think there's so much that could be said about them. But I think another underappreciated thing is this concept of prompt programming, which is a fundamentally new way that we have kind of accidentally created for interacting with these types of models. So if you think about how you interact with typical ML models, usually you have a very clear protocol of what these models can do and what they cannot do. You have an ImageNet model or something that can recognize 1,000 different breeds of dogs or whatever. You give it an image, it gives you a class. That's it. But with these models, it's really kind of wild that with these prompts, you can be way more creative than that. So prompt programming, this idea is of finding the right prompts to allow it to solve certain tasks. So the amazing thing about these GPT-type models is that you can get them to solve many kinds of tasks that they weren't really trained for. Again, these models were only trained on unstructured, unlabeled, just a pile of stuff from the net. And they can write stories in specific styles. They can write poetry, or they can work as chatbots. They can summarize text. They can even translate. Are they state of the art in these things other than the writing stuff? No. Of course, if you build a custom pipeline for translation or something, it's going to outperform your cobbled together GPT-based system. But it's kind of crazy that this works at all, ever. That's really the important thing. It's not that it's state of the art, but just that these models picked up these skills without any kind of labeling or specific handholding. And this whole concept of prompt programming is so different from how we used to interact with these models, is that we don't have to create a writing model and a summarization model and a translation model, but just by asking this model, earlier, I explained with my friend in this video game, we just asked the model, hey, please do the thing we need you to do, and it just did it. What the hell? It's just crazy. Give you one of my favorite funny examples. So friends of mine wrote a paper about this, where they showed that in the original GPT-3 paper, they tested translation performance, but with a prompt that looked like English, English sentence, French, autocomplete. And it would autocomplete in French, hopefully. And my friend showed you could get better performance, several percentage points, non-trivial amounts, by instead using a prompt that looks like the English sentence is translated by the masterful French translator as. And this worked. And if you took out the masterful, it performed less well. If you just tell the model, you're super smart and solve all the problems, it works better. I don't know what to tell you. It's like, who would have predicted this ahead of time? It kind of makes sense in retrospect, is that in a way we train our models on, just a bunch of internet text, and so they kind of learn to emulate the median internet user. So if you condition them, if you tell them you're a super smart internet user that speaks perfect French, it's more, incentivized to simulate or to a better user in a sense. Probably. Who the hell knows how these things work? So, as I said earlier, also with my friend and his thing, as these models get better, pretty amazingly, prompting becomes more easy. Again, it's worth stressing how non-obvious this was ahead of time. Is that, again, same architecture, same model, just more to compute. They just gets it. Like, this is something that people who use GPT-2 and GPT-3 will always say, is that GPT-3 just gets it far more than GPT-2. GPT-2 gets confused, gets off track or something. But even if you don't really explain what you want perfectly, or you make a typo or something, very often GPT-3 will still get what you want and still produce a pretty decent output. And we even have some data on this too. So in the original GPT-3 paper, we saw this really crazy graph here. And what we're seeing here is few-shot performance. So few-shot performance is when you give the model multiple examples of the task you want to do. So for example, if you want to solve a math problem, you might give it a few example already solved math problems to show it what you want it to do. And with the green line here, this is GPT-2, we can see that even as we give it more examples and such, it doesn't really make a difference. The model just doesn't get it. But this absolutely ridiculous blue line here shows, is the largest GPT-3 model, is that as we give it some examples, as we tell it what we want, we have this massive spike in performance. Again, this is not to be training, this is not with extra data, this is just telling the model what you want it to do. And you have this huge difference in performance here. Recently, we've had even more crazy stuff emerge with the emergence of prompt tuning, what's also called soft tuning, where instead of writing your own prompt by hand, you basically let your algorithms find the perfect prompt for you. And what we see here is the most efficient way to get good performance of your model is always going to be fine tuning, always getting data, training your model specifically on that task. That's the orange line here. The blue line here is our prompting, so it's human-crafted prompts. And here, too, we can see as the models get larger, using the same prompt, the performance increases. But what we also see is this green technique, where we use algorithms to find the ultimate prompt for our tasks, and that it actually reaches equality with full model fine-tuning. So we get the performance of a custom-built model on our task just by asking our model the right question, so to speak. I find this truly remarkable. So what are some of the key takeaways from scaling laws? Scaling these transformer models shows smooth scaling laws and performance with no obvious limit in sight. And the current models are still infrahuman on many tasks, still many things they can't do right, but we can't also be that sure. So as I just showed you with the prompting, is that the performance really depends on the prompt. And one thing that often happens is people they use GPT-3 for 5 minutes, they put in a terrible prompt, they're like, oh, look, the model's stupid. But someone who's really good at that, or use prompt tuning or something, can often get so much better performance out of this. So GPT-3 may well be much smarter than we think it is. Sometimes I jokingly say that these large models kind of feel like alien artifacts that kind of just fell from the sky one day, and we're banging rocks against them trying to make them do something useful. I don't think we've yet really understood how to get the maximum performance, even out of the models that we have today. And it's definitely possible that there is a large overhang in the amount of hardware and data that could be deployed to these problems. Sure, GPT-3 is huge and was very expensive. It cost millions to train GPT, just pure training costs. But that's totally within the limits of large mega corporations or God forbid governments or military agencies. So if someone really wanted to build a much bigger model, it definitely would be possible. So it's definitely possible that in the near future we will see even larger improvements here. So what does this mean for the future? I really think that large general-purpose models will be the basis for many, many applications in the future. So Stanford recently released a piece where they dubbed these as foundational models. Is that you'll have a backbone of these very large general models, and then you build specific applications on top of them. You build pipelines or specific prompting or fine-tunings on top of them for the specific task you want to solve. I think this is going to be very common in the future. Training these models, unfortunately, will become increasingly expensive and inaccessible. I don't like this, I don't endorse this, but this is just a matter of fact, is that if scale continues to pay out, if just adding more GPUs just makes the model better, then by definition, the best models will be available to those who have the most resources to deploy to build them. So this is unfortunate, but it's even, don't get me wrong, we should definitely work on making our models more efficient and whatever, but even if you manage to make your model training, say, 10% more efficient, that just means that the big guy can train a 10% larger model than you. I think we're entering an era of high-energy ML. So this is this word kind of comes from the idea of high-energy physics, and that we computer scientists are very spoiled, have been very spoiled for a very long time. We're used to a grad student with a laptop just being able to sit down and work on cutting-edge work right there, right then. And in most other fields, such as physics, that's not been the case for a very long time. If you're a particle physicist and you want to do cutting-edge work, you need access to massively expensive, particle colliders or other expensive hardware to be able to do the kind of work you need to do. And it seems likely that we might be moving into a similar direction in AI. Is that if you want to do this specific kind of work, there was also going to be low-energy ML work, of course. There's still going to be lots of other work that can be done on a laptop. But if you want to do this type of work, it might just be the case that you will need access to large amounts of hardware that is just, not affordable for individuals and the like. I think what is likely to be a more and more common business model in the near future is going to be that large corporations will rent out large models as the basis for other products. We're already seeing the prototypical version of this with OpenAI, where they only give you access to GPT-3 through an API. And I think this is going to be, and then other companies build products, they build chatbots or whatever they happen to build, or video games or whatever, on top of the API. I think this is going to become more common as only these large corporations, think Amazon, Google, Microsoft, will have the resources to build and deploy these kinds of models. And then smaller companies will then probably rent them and then build custom-based solutions or products on top of these models. This is unfortunate for many reasons, of course, and this is a large reason of why Eleuther AI exists. How Eleuther AI started is that we saw GPT-3, and literally in a chat room, I was hanging out with a few friends. And I was like, "Hey guys, let's give OpenAI a run for their money like the good old days." And then another friend replied, "This, but unironically," and the rest was history. And so Eleuther AI was born. So as I said, we're an open source group building large language models. So we have basically built some of the best large open source language model, Apache license. You can download them right now. And we're working on successively larger models. We believe that these models will be very important for the short, medium, and maybe even long-term future. We think these models are going to be, in many ways, how the future AI products are going to be built. They're going to revolutionize a lot of industries. And I think there is a very real chance that these models might already have, whatever the first, transformative, powerful, general-purpose AI systems turn up to be, I think there's a good chance that they will look very similar to these systems. They will at least have these big, general-purpose backbones somewhere in their construction. So I think it's very important to try to understand and to these models and how to use them correctly. So if you want a longer philosophical treatise about why I think releasing these models is a good idea, I've wrote an essay on that. You can read that if you want. But so in short, on the one hand, it is of course important to help more people utilize and benefit from this powerful new technology. It's pretty crazy. One time, a friend of mine who's Indian, he commented that the amount of computing power that we had access to at Eleuther through sponsors is more than the entire country of India's best supercomputer. So it's kind of crazy that there's a disparity here in a sense of how of getting access to these models is that you kind of have to work for these big mega corporations to even have access to these models, to even be able to do research with them or do useful things at them. And I think it would be very important to make these things more accessible, of course. I do hope that academia is going to pick up the slack here at some point. They haven't so far, but I think there's some movement starting to happen there. So I hope that similar to how academia has in the past, built super colliders and whatever. I hope that they will also start building with public money large supercomputers and large language models and large AI models in general for more people to use and research. I think this is really important work. It's actually quite funny. The other day I was talking to someone working with the Summit supercomputer, and they commented how there's really no AI project running on the Summit supercomputer, which is one of the strongest supercomputers in the world, and one of the few that actually has the perfect architecture to do AI work on. And I found that rather surprising. Don't get me wrong, there's a lot of important work being done there on climate modeling and astronomy and whatever, and I'm glad that work is getting done. But AI seems like a pretty important technology for our future. So it seems that some of our national supercomputers should be working, should be put to use for this kind of work as well. So I do think that academia is going to catch up there, but they haven't so far. Overall, I think it's really important to understand that corporations have negative incentives to downplay to play the weaknesses and risks of these technologies. I think this is actually a way more important reason, is that fundamentally, if you're a corporation, this is just how it works. You build a model, it was a large investment, you want to make your investment back. You want to make money off of this thing. That's just how it works. So you will be directly incentivized to downplay, how these models might be misused, how they might be dangerous, how they might be non-functional, or and other things. So what I would want is that I would want a thriving hacker community of people. Similarly, how we now have a thriving hacker community finding software vulnerabilities. I would want a thriving community of AI hackers finding vulnerabilities in AI and finding better ways to control them, finding where they fail, where they're dangerous, how can we make them better. And that's a large part of why I do the work at Luther, actually. Probably an even bigger reason than the others is why I do this is because I want this community to exist, and I want to have. They need access to these large models, and individual hackers in their bedrooms cannot build these models. And so I hope by making these models more accessible, they'll be able to do this critical safety-related work and understanding and control work that needs to be done so that we can deploy these models in a safe way. Because ultimately, we can't stop this technology from coming. AI has unimaginable potential to change everything. It has the potential to solve innumerable problems and to improve the lives of billions. But like every powerful technology, it is a double-edged sword, and the benefits will depend on whether we learn how to wield it. Thank you.